I'd like to discuss now what is a moment of inertia. We will see moments of inertia come up several times during this course on Newtonian mechanics. Whenever you want to know what the rotational kinetic energy is of an object, some crazy shaped object, rotating about an axis, then the moment of inertia comes up. If the object has an angular velocity, omega, which could change in time, it could rotate continuously in one direction, or it could oscillate back and forth, but at any moment in time it would have a particular angular velocity, omega, then the kinetic energy of rotation equals 1/2 times the moment of inertia of rotation about that axis times omega squared. So we will see it with kinetic energy. We will also see it when we derive oscillations. And we will do problems whereby we oscillate a ruler. It's a classic problem which I will do. I have a ruler here, and I have a hole. And I have a pin here, and I put the pin through the hole. It's almost frictionless, not quite. And I offset the ruler, and I let it oscillate. When you want to calculate the period of oscillation, you will have to know the moment of inertia of rotation about this axis, and this moment of inertia will depend on where you stick the pin. And so the frequency of the oscillations, and therefore the period of the oscillation, also depends on where you stick the pin. So this is where moments of inertia come up. How is moment of inertia defined? Suppose we take a three-dimensional object, some crazy three-dimensional object. Think of it as being a potato, 3D. And I rotate this potato about an axis. Here I have a potato. And maybe I can zoom in a little bit. Oh, no, I have to zoom in. So here's a potato. Oh, that's too far. And I could stick in here a Phillips screwdriver, and you can see that it could rotate about this axis. That is sort of this axis that I have here. But of course I could put in the axis of rotation here. I have options. And then I could rotate it like so. So I have a lot of choices in terms of how I choose the axis of rotation. I could put it in here. It's not so easy. And I can rotate it like this. And the moment of inertia, as you will see, differ for different axes. Wow, I have a lot of potato juice here. So this is the axis of rotation that I have chosen here, quite arbitrarily. And I carve out here a small mass element which I call m of I. And I have to know the distance from that mass element m of I to the axis of rotation. So this is 90 degrees. And I call that r of I. I would have another one here, say some little mass element. And then I would have to know this value, r of I. And so the moment of inertia is now defined, I, rotation, moment of inertia about this axis, is the sum of all these values for m of I integrated over the entire potato, the entire object, times r of I squared. And r of I are the individual distances of these individual small mass elements to the axis of rotation.